Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Alright, step on inside, and here we are going to do a review of everything radical-based, graphing radicals, simplifying radicals, including variables, adding, subtracting, multiplying, and dividing those radicals, solving radical equations, and solving rational exponent equations. Now, that last one didn't sound like radicals, but they are involved because a rational exponent means a fraction, means dividing, and the denominator can turn into a radical. I don't think we're going to do that too much except for evaluating those portions. Calculator free on this entire thing, by the way. And apologies for the bloodshot eye. What's it called? Broke a blood vessel in there, so I hope it's not too scary. Anyway, so we're going to rummage through these problems right here. 22 of them. I want to attach the PDF online for you guys. And you know, actually the first 6 problems here, I'm going to do a little bit of trickery here. I recorded an older video that had these 6 problems. Among them were graphing rational functions and doing things like that. So I will find that video, I'll re-download that video on YouTube, but I'll edit this, I'll stitch that part in so I don't have to do this part again. I'll let the video do that, no broken blood vessel, anything like that. I'll just talk through those, and I'm just going to go ahead and start teaching these ones in a little bit with you guys. So hang tight while I do my editing stuff and let this part go right in, and I do it for you from when I did it over a year ago or whenever it was. All right, enjoy it. I'm just going to go ahead and jump straight into it, guys. Simplify each expression completely, numbers 1 through 6. So starting with number 1, I do have a negative exponent, and it is a fraction. Now, I'm going to start with that negative portion and just talking about it here. Well, actually, you know what? Let's do 2 and 1. Yeah, let's do 1 and 1. I got enough space. Let's start by turning it positive by flipping this fraction on its head and turning it into 5y to the 4th divided by 4x squared. And that's what's happening here, and this is raised to the positive 1/2 power. Now, raising to the 1/2 power does mean taking the square root, right? Raising this to the first power and then the second root of that. So that does mean take the square root of these things. Technically, we're taking the square root of everything. I'll just split it into top and bottom, but we're taking the square root of 5y to the 4th divided by the square root of 4x squared, which again does mean you are taking the square root of everything in here. You are taking the square root of 5. You are taking the square root of y to the 4th. That's a 4. You are taking the square root of 4, and you are taking the square root of x squared. Now, I don't happen to be writing that 2 that would represent a second root right here. I'm not writing it, but you will have to remember that that does mean that you are then dividing your exponents by 2. That's clearly what the rational exponent was telling you, and some people would probably prefer to see it that way. When you multiply 4 by 1/2, you're dividing by 2. 2 times 1/2 dividing by 2. I put it in square root form. I'm going to have to do that with numbers, so here it is. The square root of y to the 4th, 4 divided by 2 is 2, so that becomes y squared. So on the top, I get y squared. And there's still the square root of 5. See, I can't take the square root of 5, so I'm going to leave it like that. We'll see that a couple times in here, I think. The square root of 4 is 2, and I'm going to turn that into that down below. And the square root of x squared is just x, as, you know, there's nothing. 2 divided by 2 is 1, and that's what we keep it as. And this is as simplified as we can get. The y's and x's can't interact with one another in any sort of way. Neither the root 5 nor the 2 can. So we're just going to leave it like that, and that is your final answer. Yes, sometimes answers do have radicals with them. Okay, number 2. 2x squared is all being raised to the 4th power, and then we're taking the square root of 27x to the 27th. So raising to the 4th power does mean you are raising the 2 to the 4th power as well. To put it bluntly, it is 2 to the 4th times x squared to the 4th. Now, in doing the square root of 27, remember, this is going to be a split. I'm going to be doing square root of 27 separately from the square root of x to the 27th. When I'm doing the square root of 27, it's not a perfect square, but there is a perfect square factor that exists inside of it. And just like x to the 27th, we're not taking the square root of this 27, we're dividing it by 2. But it's also not a x to the 27th isn't a perfect square because 27 doesn't divide by 2 evenly. So there's something we're going to have to do there. 2 to the 4th is 16. X squared to the 4th is not x to the 16th, it is x to the 8th because we do 2 times 4. So that's going to be x to the 8th power. Now we're multiplying this by, see, root 27, I can turn into the square root of 9 times the square root of 3. And I do this because I'm finding a perfect square factor that I can take the square root of, which is 9. 3 I can't take the square root of, so I'm not going to. When you do this 27 divided by 2, you think of it kind of like long division, and the thing that you can pull out is the quotient. The thing that is inside is the remainder, the thing that remains. 2 goes into 27 13 times. That becomes x to the 13th there. And the thing inside the square root, what remains is just an x to the first power. See, we took the square root of, again, that's a 2. We took the square root of x to the 27th. 13 times 2 is 26, plus the 1 remainder stays inside there. So x to the 13th root x. Sometimes the way that people split it up is they turn it into square root of x to the 26th times the square root of x, which is still the square root of x to the 27th. But dividing this by 2 gets you that x to the 13th right there. So hopefully that's helpful as well. One thing I want to mention before I keep moving forward, somebody might confuse this with a fourth root, like instead of like treating this separately here and then right here thinking fourth root of that. If they do have a fourth root, it would be more above the radical. Look right here. See that 4? It would be more above the radical right there compared to just to the left of it. So just to not confuse you with what's what. I could have put a dot symbol to indicate multiplication, but I did not. Okay, the square root of 9 is 3, right? This is 3. So 16 can multiply with that square root of 9, with 3, and that gives you 48. So I get 48 right there. X to the 8th can multiply with x to the 13th, and there the exponents add, and you get x to the 21st power. Now the root 3 stays inside the radical, and the root x stays inside the radical. They will remain inside a radical together to get root 3x, and that is your final result. For my students concerned about some of these problems, I mean, this is not way overzealous, but the idea is that the practice exam problems will be harder than the actual exam problems. That's just the nature of them. All right, number 3, I have this quantity raised to the 1/2 power and this quantity raised to the negative 1/3 power. I'm definitely going to address that negative 1/3 power given that negative, and I'm going to end up moving it down in a fraction. It'll become 64x cubed y to the 9th to the positive 1/3 power, so let's just go ahead and write that. And right now I might already turn this 1/2 into a square root there. So square root of 4x to the 10th, y squared. And hey, maybe it's the time. This is going to turn to the positive 1/3 power in the denominator, right? So that also means cube root. So cube root of 64x cubed y to the 9th. So it turned into a positive 1/3, and a positive 1/3 power is a cube root. So square root on top, cube root on bottom. Let's start taking roots. The square root of 4 is 2. The square root of x to the 10th is x to the 5th. And the square root of y squared is y. The cube root of 64 is 4. The cube root of x cubed is x, and the cube root of y to the 9th is y cubed. Again, we are dividing by those numbers there. Square root is the second root. Keep that in mind. Now we can simplify a little further here, right? 2/4 can reduce to 1/2. So a 2 on bottom, a 1 on top, but I'm going to have something else here. Generally, we don't put a 1 if there's, so I'll erase it in a second. X to the 5th over x, I can remove the x down here, remove an x up top, and you have x to the 4th. Hold on, I lost my color. X to the 4th, like that. That means that that 1 is effectively gone. 1x to the 4th is also x to the 4th. You can have it either way. And then the y, I can remove the y from the top and 1y from the bottom, and I'm left with y squared on the bottom. So as far as simplifying goes, of course, reducing fractions, among other things, that would be your result right there, x to the 4th over 2y squared. All right, number 4, kind of strange dealio with a bunch of fractions here. Now, I can't interact anything here and here until I deal with the square root, right? It's order of operations. Square roots identify with parentheses because it's a grouping, as well as square brackets would and anything like that. So, or it's like an exponent. Let me put it that way. Let me do this right now because this is going to be ever too important for us. I'm going to rewrite this so that instead on top I'm raising to the 1/2 power. Now you saw in previous problems where I was turning a this into a square root, and there are two reasons to that. Number one, they were easier numbers to divide by 2. What's 11 halves divided by 2? That's not something we really mentioned. Number two, we had numbers to deal with as well. So there are reasons why you might turn something into a square root versus not, or versus a rational exponent. But in this case, I think I'm more comfortable with doing this because I want to multiply these by that 1/2. And I'm going to spell this one out a little more here over time. So the thing I was trying to mention before is order of operations. Forget grouping and such. This is an exponent, right? It still goes before division. Exponents go before division. Now that 1/2 there we are basically going to be raising this to the 1/2 power and this to the 1/2 power, which means the 1/2 multiplies by the 11/2 and by the -1. So right here, x to the 11/2 to the 1/2 is x to the 11/2 times 1/2. And 11 times 1 is 11, 2 times 2 is 4, so you get x to the 11/4. And then y, -1 times 1/2 is -1/2. So this is y to the, -1/2 power. On bottom, I have x to the 3/4 times y. I'm sorry, that should be a y right here. Times y to the 3/2. Okay, I wouldn't convert to rational or to radicals right now. I would definitely look at subtraction anytime, I did the whole removal thing here. The removing idea is a subtraction basis. When I remove the x here, I've subtracted 1 from the bottom. I did 5 minus 1 to get 4. And, like that. So right here, as you're working this is x to the 11/4 minus 3/4 power times y to the, do I want to, you know what, I'm going to deal with the y in the denominator. I didn't even see that was negative. Let's take this here and bring it to the denominator, so it's y to the positive 1/2 power. So now when I'm doing this here, I'm subtracting up top, and I'm really dividing down below. So this is all divided by y to the 3/2 plus 1/2 power, and they're in the denominator. They're in the denominator. That's why we're doing it down there. And why is this in the numerator? Because I'm dividing. I'm taking something divided by something else, and that leads to subtracting of exponents. It's just a numerator result. These are just denominator values right now. So okay, 11/4 minus 3/4 is 8/4. 3/2 minus 3/2 plus 1/2 is 4/2. So what is 4/2? So 8/4 is 2. You get x squared. And 4/2 is 2. Excuse me, 8/, did I say that right? Yes. And you get x squared over y squared there. Number 5, let's find a color I haven't used. Number 5, the 4th root of 81 x to the 5th y to the squared z to the 8th divided by 36. The square root of 36 x to the 18th z to the 20th. Taking a 4th root of 81 is 3, and then taking the 4th root of these things here, we would divide them by 4. Now 5 can't divide evenly into 4. 4 goes into 5 once, so I can pull out an x from there. Now what will remain inside here is still a 4th root of x. There is still an x to the first that remains. That's the remainder. 5 divided by 4 is 1, remainder 1. The 4th root of y squared, I can't pull any of those out. 4 can't go into 2 at all. So the y squared still remains inside of that radical with those. And then the z to the 8th, the 8 divided by 4 is 2. You get z squared. Ultimately, that's going to kind of hang out over here with the others. I just did this in order. And then divided by down here, we have the square root of 36 is 6. The square root of x to the 18th, 18 divided by 2 is 9, so we get x to the 9th here. And then the square root of z to the 20th, 20 divided by 2 is 10, so you get z to the 10th. So, okay, that's just an x to the first, keep in mind. That 4th root has to do with that part there. So as far as reduction goes, 3/6 is, once again, another 1/2 here, and it looks like I don't have to write the 1 on top because other things are going to be up here still. But not the x, because I removed that x from there. I removed 1x from here. I'm left with 8. And not the z's. I remove both the z's from up here. I remove 2 z's from down here. I'm left with 8 z's down here. So the only thing that remains up top is this 4th root thing. It's 1 times the 4th root of x, y squared. And on bottom, I have 2x to the 8th, z to the 8th. Oops. I'll take that. 2x to the 8th, z to the 8th. Now I can't work these. There are ways you could try and do some more subtraction stuff and all that, but you just be left with negative exponents or radicals in the denominator. We're good there. If there's nothing you could pull out from this part here and there aren't multiple radicals involved, as long as I took care of the x's that are all on the outside and the z's on the outside and stuff, I'm good. That's as simplified as we're really going to get. All right, lastly, number 6. Lighter green. Number 6 here. First of all, y to the 0 is 1, so I'm just going to already just cross it. It's gone. It's 1, and any of that times 1 is anything. And this negative exponent right here, you know, I really like to work on simplifying things inside of the quantity before I really deal with what's outside, unless it's something like a negative and I have to flip it, which is exactly what we're going to do. So on top of this is only an 8 inside of this quantity, as the x to the negative 6 move down here, become x to the 6th. And I have z to the 9th right here, and we're raising this still to the 2/3 power. Y to the 0 was 1. It's gone. Over here, I can turn this to the first power, positive first power, by flipping this into x to the 8th z divided by 4, like that. To the first power, you know, just means just this thing right here. So once I get this thing out of its parentheses and its, you know, radical and stuff like I'm going to convert it to a radical. All this kind of stuff here that I'm really taking care of. You know, actually, here, I'm going to do this first. I'm going to say this is 8 to the 2/3. So you're raising everything here to the 2/3 power. 8 to the 2/3 power, x to the 6th to the 2/3 power, and z to the 9th to the 2/3 power. As long as that 2 is involved, I think taking 2/3 of a number is easier here, and I can convert this to its radical form. This is once again times x to the 8th z over 4. Now, 8 to the 2/3 power, that one I will definitely convert for us here. That is the cube root of 8 squared. Running out of room on this problem. Times x to the 8th times z. On bottom, x to the 6th to 2/3, we do 6 times 2/3. 6 times 2 is 12. 12 divided by 3 is 4. 2/3 of 6 is 4. You get x to the 4th power. Oh, by the way, there's a 4. Let me write the 4 kind of first here. That 4 right here. So we got a 4 there. Times x to the 4th times, and 2/3 of 9 is what you're doing there. 9 times 2 divided by 3 is 6. So you get z to the 6th power. So all that's left here is kind of some reduction. We still got to simplify the cube root of 8 squared. Again, running out of room, my bad. All right, the cube root of 8 is 2, and 2 squared is 4. So you're left with 4 on top, 4 on bottom. The x to the 8th over x to the 4th. Remove all 4 from bottom, remove 4 from top, you're left with 4. Remove the one z from the top, remove a z from the bottom, you're left with 5 on bottom. So the 4 over 4, by the way, is going to become 1 as well. Those are going to go away. All that you're left with is x to the 4th on top, and it looks like z to the 5th on bottom. Honestly, that is the end result. X to the 4th over z to the 5th. Nothing else involved in it. That is definitely much further simplified than the stuff that we had before, right? That surely cleaned up. Whereas these other ones are like, did we really clean this thing up? Is it much better than it was before? I don't really know. All right, so there's that. All right, so that's the exponential property stuff, playing with that again. It's, you know, being a little creative and just trusting the process and boxing it when you feel you're out of parentheses and, you know, radicals and stuff like that. Okay, and we are back here. So whatever I did on that 1 through 6, I hope that it was very helpful. Let's move on to number 7 through 12, where we're going to add, subtract, multiply, and divide, and simplify as a result. So in this first problem here, root 18 minus 2 root 27 plus 3 root 3 minus 6 root 8. Whole goal is to get it down to any perfect square factors that are in there, factor them out. Square root of 18 is root 9 times root 2. Square root of 9 is 3. We got 3 root 2 right there. Square root of 27 is square root of 9 times square root of 3, and that's times that 2. Square root of 9 is 3, and 2 times 3 is 6, so minus 6 root 3 right there. Square root of 3 can't be broken down anymore, so that's going to be a 3 root 3. And square root of 8 is square root of 4 times square root of 2, and that breaks down into 2 times 6, which is negative 12 root 2. I was finding perfect square factors there. 9's a perfect square, 9's a perfect square, 4's a perfect square. 3 contained no perfect square factors in there. So now we can combine like terms. 3 root 2 minus 12 root 2 is negative 9 root 2. And negative 6 root 3 plus 3 root 3 is negative 3 root 3. And that's as far as we can simplify that. All right, the same thing's going to happen here on number 8. The difference is now we're talking about cube roots, so we need perfect cube values. That's like 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, and so on and so forth. You find those factors inside here. 16 is a perfect square, but not a perfect cube. 8 is a perfect cube, however. And if I multiply this by the cube root of 8 times the cube root of 2, Cube root of 8 is 2. 8 times 2 is 16. You get 16 times the cube root of 2 there. And this plus 2 times cube root of 2, that can't really change, so we'll leave it like that. Minus. 375 is 125 times 3. 125 is a perfect cube. It's 5 cubed. So root 125, cube root 125 times cube root of 3. Cube root of 125 is 5. So that becomes minus 5 root cube root 3. It doesn't seem like that can combine with either of these. Oh well. These two will combine together and we get 18 times cube root of 2 minus 5 times cube root of 3. You still simplify it. The whole goal of simplifying is to attempt to achieve and to combine those things. And if they can't, at least you still simplified it and we're good there. We're done. Okay, number 9, we have multiplication going on. Now, there are two ways we can go about this, or kind of multiple within. We could distribute straight up right now. I'm probably not going to end up doing this, but root 24 times root 6 we got to do, which would give us, I think, root 144. Actually, that's not too bad. Root 144, that's a perfect square. And then minus square root here of 192. 192 right there, and then you have to break those down. Square root of 144 is 12. Root 192. What's the largest perfect square factor? That's the problem. 24 times 8. See, that's the thing. I guess 64. So root 64 times root 3 would give us root 192. So you see, you have to hunt for that, and that's without a calculator. That'd give us 8 root 3. And I'd be done there. I mean, that took a little bit for me to figure out and kind of come up with that. So let's break it down smaller. Let's instead turn it into root 24 is root 4 times root 6. That's 2 root 6. Then multiply that by root 6 minus square root of 8 is 2 root 2. I think we did that a little bit ago. And now when we distribute it here, 2 root 6 times root 6, root 6 times root 6 is 6. 2 times 6 is 12. Root 6 times root 2 is root 12. 2 times 2 is 4. That's 4 root 12. Square root of 12 is square root of 4. Oh, right here. Oh, we didn't do it. Root 4 times root 3, so that's 2 root 3. 4 times 2 root 3 is 8 root 3. So 12 minus 8 root 3, and we get it again. So, you know, like that's kind of the thing. If you break them down into smaller things, that will be very helpful. That's kind of that's how I'd want to go about that problem, at least the gist of it there. A lot of other things you could do in between, but that's really what I was going for. All right, number 10. 2 plus root 5 times 5 minus root 5. This is straight up FOIL action. First, outside, that's 10 minus 2 root 5. Inside, last, that's plus 5 root 5 minus root 5 times root 5 is 5. 10 minus 5 is 5. Negative 2 root 5 plus 5 root 5 is 3 root 5. And done. Number 11. This is kind of similar to, well, let me talk about this first. Our goal is to rationalize the denominator. 24 itself is not a perfect square. I can simplify it, and listen, I'm going to eventually, but I just want to first make mention that it's, right now, it's not, it's not like root 25, which would turn into 5. Root 24 would be 2 root 6. So it'd still have an irrational. So to rationalize the denominator, we'd have to multiply top and bottom by the same thing. Now, I will not end up doing this method because we'd have to distribute this here. We'd have to do 24 times 27, simplify that square root, and then possibly and still reduce a fraction, still reduce the denominator numerator stuff. It's way too much. I still have to reduce the root 24 with the 9. Let's reduce now and simplify now, and let's do it even with that root 27 as well. So root 27 is 3 root 3. Root 24 is 2 root 6. This helps me a lot because now I don't have to multiply by root 24 over root 24, but just root 6 over root 6. And that'll still rationalize the denominator. Maybe I still have to simplify things. I don't know. But that'll at least get me started. Now, the root 6 must distribute into these two because that's a quantity that it's multiplying by, right? 2 root 6 times root 6. I think we just saw that in the other problem there. That's going to be 12. Root 6 times root 6 is 6. 2 times 6 is 12. And we've rationalized it. Now we have 9 root 6 up here. Cannot simplify. Root 3 times root 6 is root 18, which can simplify. Square root of 18 is, and by the way, you might notice these can all divide by 3. Just hold on for a second because we got to simplify this still. Root 18 is 3 root 2. So 3 times 3 root 2 is 9 root 2. And then these can now all divide by 3 right here. And we should be getting here 3 root 6 minus 3 root 2 over 4, all over 4. And don't try and take the 4 and reduce it with the 6 and the 2, because that's not a 6 and a 2. It's square root of 6. That's around 2.5, somewhere between 2.4 and 2.5, and root 2 is around 1.4 something. They're not really those numbers that we're talking about, right? So don't reduce them. We're dead. Number 12, similar. I don't want to multiply. A couple things. The root 7s do not cancel. You don't just go like that. You're done. No. I've said too many times why you can't do that. Just don't. You can't. Stop. We can, however, and we can't also just say, hey, let's multiply by root 7 over root 7. That'll do the trick. See, the problem is, remember how this distributed up here? The root 7 would distribute down here. And while root 7 times root 7 is 7, 2 times root 7 ain't rational. That didn't rationalize it. The way that we're going to have to rationalize this guy is multiply top and bottom by the denominator's conjugate. The conjugate being, if this is a minus b, we got to multiply by a plus b. That'll give us a difference of 2 squares, a squared minus b squared. It leaves us with all rational things down below. So let's multiply top and bottom here by 2 plus the square root of 7. 2 minus root 7 times 2 plus root 7 as binomial quantities there distribute very, very nicely. That becomes 2 squared minus root 7 squared, or 4 minus 7. 2 squared is 4, root 7 squared is 7. On top, we got to FOIL this thing here, multiply that out. 1 times 2 is 2. 1 times root 7 plus 2 times root 7. Root 7 plus 2 root 7 is 3 root 7. And root 7 times root 7 is 7 right there. 2 plus 7 is 9. That's plus 3 root 7, all divided by negative 2. Now this would be done. There's no fraction to reduce here, but the fraction shouldn't have a negative denominator. You can factor that negative out, apply it to the whole fraction, or distribute it into the top, which is what you more so see on problems like this. So negative 9 minus 3 root 7 over positive 2. That's going to be my end. Look-see right there. Some teachers might be fine with that. I'm not. The math gods are not when it comes to simplifying there. I just want to make sure I did everything else right. 4 minus 7 isn't negative 2. It's negative 3. So that's... Oopsie. Okay, so I might have said 5 minus 7 in my head. I don't know what I was doing. All right, let's do that again. Divide by negative 3. Hey, those can all divide by negative 3. Let's do that again. 9 divided by negative 3 is negative 3. See how it turned negative? 3 divided by negative 3 is negative 1. All right. I was thinking that when I made the problem that I made it prettier and cleaner than what I had without the fraction reducing. A lot of people were probably yelling at the screen saying, go back. That's okay. All right. Moving on. Back page. Here we go. Solve check for extraneous solutions on 13 to 15. Be cautious of possible 2 solution cases on 16 through 18. Got it. Number 13, we got to start by isolating our radical right here. We got to add 2 to both sides before we square both sides on this thing. Now we're going to go ahead and square both sides, and isolating the radical allows us to achieve eliminating the radical there. We're taken care of. Square root of x minus 3 squared is x minus 3. 2 squared is 4. Add 3 over, we get x equals 7. We can check it out. It should work out. 7 minus 3 is 4. Square root of 2 is 4 is 2. 2 minus 2 is 0. It's good. On this one, we got to isolate one of these radicals first here before squaring both sides. If you square it right now, you come up with a perfect square trinomial that leaves you with double sets of radicals, which are no good. So I'm going to add 3 times, 3 times square root of x minus 6 over to the other side. And we'll get root 3x minus 6 equals 3 root x minus 6. Fun stuff. Now, when I square both sides right here this time, remember, this is a product over here. This is 3 times. Oops. It's 3 times square root of x minus 6. So we're going to square the 3 as well as the root x minus 6. Like, I couldn't fully isolate it, but I'm good in this form right here. There are going to be no radicals left. Here I have 3x minus 6, and here I have 9 times the quantity x minus 6, like that. Right, 3 squared is 9, square root of x minus 6, and it multiplies. So 3x minus 6 equals 9x minus 54. I'm going to subtract 3x, and I'm going to add 54. Was that 48? So we get x equals 8. Let's double check that. I don't trust my own math there. 24 minus 6 is 18. Square root of 18. Hold on. That becomes square root of 18 here. I'm going to do it based on this one because I like the left side and the right side kind of being separate instead of equals 0. So equals 3 times 8 minus 6 is 2. Square root of 18 equals 3 root 2. Yeah, root 18 is root 9 times root 2, which is 3 root 2. So 3 root 2 equals 3 root 2. That does check out. And listen, if they were way different numbers, then I got a wrong number. It's not extraneous. I got the wrong answer. If they were opposite signs, then that's when it's extraneous, if I did all the math right. All right, right here we have an isolated radical, root x plus 22, and on this side we have 3x minus 4. I will square both sides right now, but this time when I do it, we're going to run into a little perfect square trinomial here. We got a squared minus 2ab. 2 times 3x times negative 4, or times 4 is 24x, minus 24x plus 4 squared, which is 16. It's a bigger perfect square trinomial. Haven't done many of those. And square that square root, it goes away. I'm going to subtract x over. Subtract 22 over. What is that? Negative 6. No GCF to speak of, but we're going to try and factor this guy out. It's either 9x times x or 3x times 3x. I honestly don't know which one. I'm going to go for 9x. Looks like 25 is a pretty large number there. 9x and x right there. If it's not factorable, then we're going to have to go with solving using other means there. So 6 and 1, no. 3 and 2, yeah. So minus 3 plus 2. This will give us negative 27 plus 2 is negative 25. So if 9x plus 2 equals 0, you would subtract 2, 9x equals negative 2, divide by 9, x equals negative 2 ninths. Here, you add 3, x minus 3 equals 0, you get x equals 3. Now I'm going to double check for extraneous solutions, and in doing so, you're going to substitute those values in. Now, all I'm really checking for, I already mentioned this before, all I'm really checking for is to see if the left side is opposite of the right side, because my answers are right, like as far as the quadratic portion. I got to see if the left side is the same as the right side or opposite sign of it. If it's opposite sign, it's extraneous. Let's try 3 first. We got 9 minus 4 is 5. Square root of 3 plus 22. Square root of 25 is 5. 3 is good. Negative 2 ninths, I can already tell you it's not going to work. And here's why. I'm going to do 3 times negative 2 ninths. I don't care what it is. I'm going to tell you why. It's a negative number. Negative number minus 4 is still a negative number. On the right side here, I have negative 2 ninths plus 22, which is positive. Square root of positive is positive. Here I'm going to get something that says negative equals positive. That's not going to work. Negative answer, and negative number never equals a positive number. So we're not talking about real numbers. So whatever it is, it's going to be the exact opposite of the other, square root, whatever. That one's not going to work. Not because it's a fraction. It just doesn't work for the problem. That one is extraneous. Without actually doing a real substitution, I can tell you that for sure. Just 3 is the only answer there. All right, number 16. This is where we now have rational exponent equations here. You want the quantity here isolated, which it very much is, and then we can raise it to the reciprocal power, raise it to the 3/2 power there, and raise this to the 3/2 power here. 2/3 times 3/2 is 1. That's what leaves us with just 3 plus 2x over here. But keep in mind, raising to the 3/2 power means taking the square root of both sides. If this thing inside here was to be squared, then that means this could have been positive or negative. So we are referring to the plus or minus version of whatever 9 to the 3/2 power is. Now for 9 to the 3/2 power, we got to do the square root of 9 and then cube it. Square root of 9 is 3. 3 cubed is 27. So we're plus or minus 27 there. So we got to subtract 3 over. And then we got to divide by 2. Now these are numbers that we can get. Like we can actually evaluate what these are. What's negative 3 plus 27 over 2? What's negative 3 minus 27 over 2? Negative 3 plus 27 is 24. 24 over 2 is 12. Negative 3 minus 27 is negative 30. Negative 30 over 2 is negative 15. So 12 and negative 15. I'm going to trust those are correct. I'm not going to actually do the math on that. That should be good. But keep in mind, well, here, you know what? Yeah, let's do the math, because let's talk about the plus or minus aspect. Why did this happen? What changes from here? There's no extraneous solutions. I'm doing this to show you what happens here. 12. 2 times 12 is 24. 3 plus 24 is 27. We raise 27 to the 2/3 power. That means we take the cube root of 27, which is 3, and 3 squared is 9. Okay, that one works. Negative 15. Why does this one work? 2 times negative 15 is negative 30. 3 minus 30 is negative 27. You do negative 27 to the 2/3 power. Cube root of negative 27 is negative 3, and negative 3 squared is positive 9. You're squaring a negative number out. As long as this is squared to the 4th or to the 6th, you can have a negative answer as a result as well. That's why I said those even roots will generate a plus or minus for us right there from that. These other problems don't look like they're going to have that problem. So we move forward. This next problem here, we are going to isolate 6 minus x to the 3/2 power by subtracting 3 from both sides. So now we'll have 6 minus x to the 3/2 power equals 8. Now that it's isolated, we can raise both sides to the 2/3 power. This being an odd root, that's not going to be a plus or minus concern for us. So 6 minus x over here, cube root of 8 is 2, and 2 squared is 4. I can subtract 6 over, and we'll switch signs, multiply by negative 1, whatever. X equals 2, we're good. No extraneous things to be worried about here. Number 18 has a few little wrinkles here. First of all, we have to isolate this thing, this guy right here. It's x plus 3 to the negative 3/4. So we got to divide both sides by 3. And you know, some of my students, let's say the x plus 3 wasn't there. Let's say it just said this right here. Okay, the same biz still applies. 3 is not being raised to the negative 3/4 power. Let's get that clear and out of the way. I'd still have to divide both sides by 3 when I'm doing that to isolate, right? So just remember that. It's not attached to the hip with that thing unless it's in parentheses, like the 3 was, which it's not. I'm going to divide by 3. Now, how do I divide by 3 over here? What's 1/9 divided by 3? It's not 1/3. You got to multiply by 1/3. I think that's the better way of looking at it there. So we have x plus 3 to the negative 3/4 power equals 1/27. That's a third smaller. That's 3 times smaller. I've talked about this before. Negative exponents right there. Let's deal with it in such a way that, well, let's raise to the negative 1st power first. Let's kind of deal with that negative portion and then kind of do the other part after. X plus 3 to the 3/4 equals 27, right? That's what a negative exponent does in this case, flips your fraction. Now we can raise to the 4/3 power kind of happily and not have that be a concern that it was. It's turned out to be a pretty clean problem. X plus 3 now equals cube root of 27 is 3. 3 to the 4th is 81. And subtract 3 from both sides, we get x equals 78. Okay. Last 4 problems, graphing. Well, 2 of them are graphing, 2 of them are writing the equation for the graph. And they say provide the domain and range for each. That's for these 2 graphs right here. First one's a square root graph right here. F of x equals negative 3 times the square root of x plus 8 plus 4. This is your form that is f of x equals a times the square root of x minus h and then plus k. Your your reference point is at hk. That also has to do with domain and range on these graphs, and a is your vertical stretch factor. It also reflects over the x-axis for this thing. We're going to start at negative 8, comma 4, that being x minus h, x minus negative 8. We're going to be at negative 8, comma 4 right there. The negative 3 is our vertical stretch. We'll flip it over. We're going to go downward to the right. Still goes to the right, plug in those values for x, and make everything 3 times larger. You go over 1, you go down, instead of 1, you're going to go down 3, triple that. Let's go 4 over. Square root of 4 is 2, but we got a triple 2, and 2 is 6. Now let's go over 9. Square root of 9 is 3. Triple that, you get 9. How many points did I allow myself to fit? We'll see. 16 over, down, square root of 4, or square root of 16 is 4, times 3 is 12. What's 12 down from 4? Negative 8. Can I fit a 5th? I don't think I... 25 away from... No. No. I think we're good. 17. Oh, yeah, we can. Oh, yeah. 25 from, yeah. From negative 8, not from 8. 25 from negative 8 is 17. Yeah, we can go over to 17 right there. And I can fit, ooh, I don't know if I can really fit that height, though. Down 1, 2, 3-ish. I'm going to kind of put it kind of like there. There we go. Plot as many points as you can fit, right? All right. And there it is. Now, domain and range are determined in a couple of... That doesn't look like it curved as much as it should have. Domain and range, you can tell by a graph when you see domain. When we talk about domain and range, is how far left and right does the graph go as domain, how far up and down does the graph go as range. So this domain is x is greater than or equal to negative 8. Now that's also determined based on this guy right here. You can't take the square root of a negative. Your domain has to state that the inside value of the square root has to be greater than or equal to 0. And you can see if you subtract 8 over, you say x is greater than or equal to negative 8. That's where that comes from. The range does have more to do with the graph, or at least your understanding of what the graph should look like here. For a square root graph, okay, for a square root graph, there is a limit of your range based on your domain. And if you know the smallest value in your domain, or the one where it ends up at its point, you could plug it in and get the range. But it has everything to do with k. It has everything to do with k right there. And because it goes downward, it has to do with a as well. It reflects over. This is y is less than or equal to 4. And again, range is determined based on your graph. Domain is based on what you can plug in for x. Range is based on what you get out for y. And yeah, there's that one right there. All right, number 20. F of x equals cube root of 8x minus 16 minus 3. Now this, this is a cube root graph this time, so I still want to put it kind of in that form. So a times cube root of x minus h plus k. Now notice that there's an 8 right there. Not only that, but it's not only inside, but it's multiplied by x, as an x minus h isn't even getting its own quantity right now. I'd want to factor that 8 out. Not just of, I'm not talking about the radical yet. I want to factor the 8 out of that x minus h bit. I want my h to be my true h value. It's actually a 2. H is actually 2 when you factor it out. And then I got cube root of this thing. This is a product in here that I factored out. I can now take that cube root of that 8. This is cube root of 8 times cube root of x minus 2. And the cube root of 8 is 2. So this becomes 2 times the cube root of x minus 2 minus 3. That's my form right there. A times cube root of x minus h plus k. Now, if I pull that 2 out, like let's say there was like a negative 7 right here, 2 would have to multiply with that negative 7, and you get negative 14. So if there is an a outside of there, make it more of an a when it multiplies by that. Now, cube root graph is not a square root graph. You go over 1 and 8 and 27 as you go up 1, 2, and 3. We're going to double those heights, though, as well. So I'm going to start at hk. That's at 2, negative 3. I'm going to start right here. When I go over 1, cube root of 1 is 1, doubled is 2. When I go over 8, cube root of 8 is 2, doubled is 4. And the next perfect cube is 27, which I can't fit. Let's go the other way. Cube root of negative 1 is negative 1, doubled is negative 2. Cube root of negative 8 is negative 2, doubled is negative 4. Can I fit 27 over? Absolutely not. So that's as best as I can do right there. I'm going to go ahead and try that again. I'm going to start from here and kind of curve both directions there. Looks okay. Now, a cube root does not have limit on domain or range. It goes forever left and right. It goes forever up and down. Even though it goes more sharply left and right than it goes up and down, the domain here is all real numbers. The range here is all real numbers. It's everything. Normally, I haven't asked my students about providing domain and range for cube roots, just square roots here. All right, write the equation. Last two questions. Write the equation for each function graphed below in this form right here. The form looks freaky. We kind of just showed the form before, but this time I'm not tipping my hand as to which one's a square root, which one's a cube root. Take a lucky guess. And this b exists right here as well. You don't have to have b. You might sort of. You can have a be your full number, your full scalar multiplier, instead of b, but sometimes b has to be included with the negative, especially with square roots. Take, for example, like this. And there's more than one way we could write this answer. So here's what we got to do. Think about how you would graph saying like, oh, if I were to graph this thing, this vertex, whatever we call it, this thing right here is at 0, 4. That's HK. That means H is 0, K is 4. And then you're thinking about things like, all right, well, what's A? And, which direction does it go? Well, it goes upward. That makes A positive. But it also goes to the left, which means B is negative. The negative B, B can be -1, for example. I could say, hey, B is -1, so it makes the graph go left. That's what kind of changes your domain that direction, having B be negative. And then A can be my vertical stretch and go like, well, we're going over 4 and we're going up 1. Normally we'd go over 4 and go up 2. Now we're going half that amount. See if that continues. We're going over 16 and we're going up 2. Normally we go over 16 and we go up 4, right? Oh, by the way, this is a square root graph. Normally we go over 16 and we go up 4. That's the square root of 16. But now we're going half that height. That must make A 1/2. So one way of using these ones to write that equation would be f of x equals, I have 1/2 for A, times the square root of, not cube root of, and B is -1. So I'd have to keep that negative outside of the x minus h quantity. So x, you know what? X minus h is x minus 0. I'm going to kind of simplify this. And plus k is plus 4. So x minus 0 is x. So I'll just put -x inside of there. Square root of -x plus 4. That's one answer. Now, there are other answers I could do to have both an A and a B, but alternatively, instead of mentioning this as a vertical compression of 1/2, you could argue that, normally we'd go 1 and up 1. Now we're going over 4 to go up 1. So we went from over 1 to over 4. We stretched this thing 4 times larger. So alternatively, you could say, A is 1. We're just going up 1. We're just going up 2. As instead of going over 4 to go up 2, we're going over 16 to go up 2. We're going 4 times larger. That's a horizontal stretch. You could mention that as well. You know what's a horizontal stretch? A B value of, well, it's negative because we go to the left. What's a stretch of 4? It's not a B value of 4. It's a B value of 1/4. It's the reciprocal guy. And this is something I don't expect as many people to put as an answer here, but here's an alternative. A can be 1. You can take the square root of, and this can be -1/4 x, like that, and plus 4. H and k are still the same, and we have that answer there. So that is an alternative. I don't like it as much. I'm not going to go with that, but it's something you can do. It's something I'm not taking away from. And by the way, let's see if that makes sense. This 1/4 is multiplied by -1 by x. If I took the square root of 1/4, what do I have? 1/2. That's where it comes from right there. So that can simplify to the other. One or the other. This or that. Okay, last question. And I'll move myself over for this one here. This one actually is probably easier than the square root one. I got a cube root one right here. I can just see it's a cube root one right there. Now my HK is the center where you're going to kind of see that symmetry from one thing to the other there, if that makes sense. So now it's at -4, 0 right there. This time K is 0. So it's a negative cube root, because normally cube roots would go that way. Sorry if I said cubic. I meant cube root. It's got a stretch. When I go over 1, I go up 4. When I go over 8, I go up 8. Instead of going up 1 and going up 2, I'm going up 4 and 8. That's times 4, 4 times larger. So H is -4, K is 0. Looks like A has to do with a 4, but because it's also flipped over, you could treat it as -4. And then you could say that B has no change. You could say B is 1, and then you're good with that. So then we could say f of x equals, now A is -4, is it flipped over and stretched, times the cube root of, and here's x minus h, x minus -4 is x plus 4. And then plus k is plus 0, so we can just kind of leave it, and then we're done right there. If you wanted B to be negative, because here's the thing, you flip a cube root graph over left to right instead of up to down. If I flip this thing left to right, it's also going to go that direction. I just flipped it left to right, by the way, not up to down. So if you flip it left to right, it's also going to go that same direction. So you can make B be -1 if you wanted to. You could say, hey, you know what? B is the -1. A is a +4. And times cube root of -1 times x plus 4. Again, would I do that? No, I don't even like it. It doesn't even look like a simplified thing there. But cube root of -1 is -1. That would go out there and multiply by that. That is fine. I'm not going to talk about B being a horizontal compression. I think that's way too much to kind of get into for cube root that would go so far out. So one or the other there. I'm really liking the top one more. But that is it, and that is all. And that is it, and that is all. So that ought to do it for this one, guys. This is Mr. Robinson. I want to thank you so much for watching this one. And if you have any questions, please let me know in the comment section down below here. And I hope that this stitched properly with that other video that played through. Hopefully there was no real loss in understanding in what happened there. If you have any more questions, please let me know. But this is the end of my radical talk video-wise. I do believe. I don't think I'm really doing anything else with this. So thank you so much, guys. Take care. And I will see you in the next one.